So hello everyone. Today we are going to solve questions from June long challenge, and here we go. So the first question is alternate addition. So in this question we are given two numbers A and B, and what we have to do, we know that A is less than B, and what we have to do is if for ith operation, if I is odd, we'll add 1 to A, and if I is even, we'll add 2 to A. So basically our question is whether can we make A equal to B. So this question is fairly straightforward. To solve this question, what we'll basically do is we'll take the difference between B and A, and if the difference is divisible difference modulo 3 is equal to 0, basically if the difference is divisible by 3, then yes, we can make A equal to B. And if difference is not divisible by if difference modulo 3 is equal to 1, and even then the answer is possible, because we add some odd number of steps, we would have added 3 times I minus 1 times 3 and additional. Yeah. So moving on to the next question. Equal strings. So in this question we are given string A of length n, and we can choose any subset of that string subsequence of the string, and change all those letters to some other common alphabet. So we had to check whether we can make it equal to some other string. How many minimum numbers of operations are required to make A equal to B. So in order to do this question, it is very simple. So if you are given a string A, if you are given a string, so if you are given a string, okay, so suppose you are given this string AB, and you have to make it CD. So what do you have to do? So basically you will make A equal to C and B equal to D. But what actually we did over here is we basically counted all the positions where we saw where for every position where string A, the character AI is different than BI, we noted down BI, and the total number of operations required will be the cardinality of a set of all those unequal numbers which we are taking. So this is how we'll do this question. So let's move to the next question. So next is divisible by I. So in this question, you are given an integer n, and you have to make a permutation of n such that so just a minute. Okay, so you have to make a permutation of n such that pi plus 1 minus pi modulo I is equal to 0. Basically, the difference between the absolute of this difference should be divisible by. Basically, the difference between I and I plus 1th element should be divisible by. So there is a very simple greedy method to do it. So basically, you want that the we can the simple approach is make the last element n. Now you know that so if this is my nth element, so n minus 1th element will have to be 1. I cannot use anything else other than this. And similarly, my n minus 2nd element will be n minus 1. So basically what I did, I took the last element as the n, and then I subtracted n minus 1, then I added n plus then I added first I subtracted n minus 1, then I added n plus 2, then I will subtract n minus 3, and keep on doing so till I get the complete array. So this is how I will solve this question. So moving on to the next question, that is possible GCD. So yeah, in this question, we have positive two different integers a and b, and you have to find. So you are given two different integer a and b. You have to find out a number of ways. Uh, uh, so basically, you have to find number of distinct values the GCD of a plus x and b plus x can take. Given a x can be any x can be any integer. So how will we do that? So basically, if you evaluate this, if you evaluate this question, the answer, the different number of values this can take is equal to the number of factors of difference of so basically b minus the difference of these number, the number of factors this guy will have, that will be the answer. So how will you calculate the number of factors of this guy? So basically, what I actually did here was, in my solution, I used a sieve of Parato's. I used a sieve method to do this. Let my code open. Yeah. So basically, I use sieve to calculate the first. So basically, I calculated like first 10 raised to three prime numbers, and I took found the factors of and I found the prime factors of that, and from that I calculated the number of divisors it has. So basically, if a number n can be represented as I raised to a, j raised to b, and k raised to c, as where I, j, k are prime. So basically, the number of factors are a plus 1 into b plus 1 into c plus 1. So this is how we need. And there is just there is one thing which you might want to look during this implementation is, so basically the number of prime numbers I got some prime numbers. So from my implementation over here, oh sorry, yeah. So from my implementation over here, you can see I will get I will get prime numbers up to 10 raised to power 5. But what if I get in my the difference which I get from b minus a is divisible by is a prime number which is greater than 10 raised to 5. So in that case, what will happen? So if I have a prime number greater than 10 raised to 6, so definitely there won't be it won't be divisible by the prime numbers which we have calculated. And in this step over here, so if the difference if difference doesn't equal 1, which means there exists an additional factor, so the number is actually a prime number, remaining a prime number. So we add another factor which is that number to our factors, and thus we get the answer by multiplying it with factors I plus 1. So that's how we solve this question. So moving on to the next question, reduce to 0. So in this question, basically we are given two integers. We can perform these three operations. So basically I can double x, I can double y, or I can simultaneously subtract one from each element. And we have to determine whether we can make both the elements equal to 0. And we have to do it in minimum number of operation, or else print if it is not possible. So first thing we need to notice that the order of the elements is 10 raised to power 18. This will be important. So we are given x comma y of order 10 raised to power 18. So one thing which we would realize. So when will when you can't reduce these numbers to a zero. So that will happen when either one of them is zero. If exactly one of them is zero, if x is zero and y is one, or if y is one or x is zero, or something like this. So you can never reduce both the elements to zero. But but if both of them are zero, both x and y are equal to zero, at that time you have already reduced it to zero in zero steps. So so basically these are the simple cases you need to handle. So after this, now how will you approach the question? So one thing you should realize, after handling these cases, we will have one number. We will have two distinct numbers. Basically, if let us assume that x is greater than y. Yeah. So let us assume that x is greater than y. Now it will be intuitive to you that no matter what you do, you will have to perform at least x number of steps, because you have to decrease x to zero anyways. So our answer will be x plus some number. Now, what is that some number? You basically have to make y equal to x. There's no point in multiplying the greater number with 2, because it will just add number of steps. So basically, the larger number will only be we will only reduce the larger element. But now, what about the shorter element? So what we can do is we are allowed two operations on the shorter element. Either you can multiply it by 2 or decrease it by 1. But how will we determine what operation do we need to perform? So for that, basically for that, what we'll do. So suppose we are given something like 29 and 7. How will you solve this? So so the greedy strategy is like to make this like keep on doubling 7 as much as you can till it gets less than or greater than half of this number, or equal to this number. It should be greater than half of this number, and less than equal to this. So basically I can make, in two operations I can make 29 as 28. Now I can reduce all the numbers 28 times, and I will get 2 comma 1. Then I multiply this with 2, then I will get 2 comma 2, and an additional 2 operations. So I will need a total of 29 plus 3, 2 operations for this, 27 operations for reduction, and 3 operations for this. So I will need a total of 32 operations for this. Now, how did I calculate this? So basically, I calculate that power of 2 due to which our number. So if x is greater than y, I calculate that power of y such that this number is greater than equal to x. Okay, so if suppose I have x equal to 7 and y is equal to 28, so for I equals to 2, I need 2 steps to actually multiply y to a greater number, and then 28 steps to drop it down. But if I have in this case I will be 2, and if I find and if I'm given something like 7 comma 29, so I will need 3 so I will need 2 steps to make it to 28, then we'll reduce it, and then another additional, and you will definitely need another step to make the 1 to 2. So basically from 7 to 29 I'll get 28 to 29, and 1 is to 2, and then 0 0. So here we multiplied this number twice. Here we subtracted 27 from both elements. Here we multiplied this by 2, and then we subtracted 0. So basically we got 32 steps. So basically, so our answer will be, so if y into 2 raised to y is greater than equal, we'll find the smallest I for which this is 2, and then our answer will be x plus I. So yeah, so that's it. That's it. The answer, and that's how I implemented this question. Oh, I'm sorry. That's how I implemented this question. So I basically noted down all the powers of 2, and according to that, my answer, I get what my answer is. So moving on to the next question. So next question is, I guess, expected move. So in this question, we are given two integers x and n. And what happens when we get head, x increases by 1, and when we get tail, x decreases by 1. But if x is equal to n, we don't get so basically x doesn't change. So basically we need to find the expected value of we need to find the expectation value of number of coin flips required such that x becomes 1. So to find the so before running into an expectation value problem, let us understand what an expectation value is. So let's start with what is a random variable. So random variable is a function mapped from sample space to real numbers. So that it could be anything. An expectation value is defined on random variables. So expectation value of a random variable, you can think of it as weighted average of it, and the weights are defined by the probability of that of the probability of it happen of that random variable attaining that value. Suppose I have a random variable x which attains the value 1, 2, 3 with the probability 1/3, 1/6, and so I guess this will be 1/2. Let me just cross check. Yeah, it will be 1/2. So so the expectation value is basically expectation value of x will be the value that the random variable takes into the probability associated with that value, plus 2 into 1/6 plus 3 into 1/2. Whatever this is, this will be the expectation value of this random variable. Now here, what a random variable is. Here a random variable is the number of steps required for our x to become 1. Now the question is, okay, now here we are also stuck with the point that okay, so if a number increases up to n, then we and if we flip the coin, then we are stuck at x. So for now, let's not consider if we are at n or not. Let's just consider a general case. So expectation of value of any number I, what will it be? So expectation number, if we are at position I, the expectation value of that, it can be written as half into expectation of I minus 1 plus 1. So basically, with the probability half, I can go to because that coin is fair. With the probability half, I can go to stage I minus 1, and I would require one step for that. So basically, so expectation value is this plus half into e of I plus 1 plus 1. So this is the expectation value for expectation value of I. So this is the recurrence relationship we have. So what I do, let me redefine our game. So suppose we have we start with a number I, like number I and t. So and we are at some x between these numbers. So t is the so assume that when we get heads, we increase x by 1. When we get tails, we decrease x by 1. Heads may increase, tails may decrease. And if we reach t, we should stop the game. And if we reach okay, let's not call this t. Let's call this guy as s. So if we reach s, we should stop the game. If we reach 1, we should stop the game. And if I get heads, I will increase by 1. If I get tails, I will decrease by 1. So what happens in this case? So considering our previous rules, we know that e of 0 equals to 0. E of s is also equal to 0 because sorry, e of 1 equals to 0 because if we are at 1, We don't need additional steps to go anywhere else. Similarly, if you are E of S, we won't need additional steps. And in the previous slide, I showed that expectation value of 2 is equal to half of expectation value of 1 plus 1 plus half of expectation value of uh, 3 plus 1. Yeah. So basically, if you do this, you will get S equations, and we have S unknowns. So from that, you can figure, like I tried for the some small value, and I got the expectation number as x minus 1 times 2 and not this, x minus 1 times s minus x plus 1. I got this as my expectation value. Now here we are assuming that so what are these numbers? These are the number of steps required to go from here to here plus the number of steps required to go from here to here. So it's basically multiplication of these two numbers. And what when now we can redefine our if we jump back to our problem of 1xn, we can, if we want to go in this direction, the number of steps are x minus 1, and if you want to come via this path, it will be basically 2n minus x 2n minus x plus 1 minus 1. So basically our expectation value becomes x minus 1 into 2n minus x. And some people might have solved this via the observation in the test cases, and I mean, yeah, that's a way to do it, but you should know the maths behind it, because sometimes it may work for this question, but if you wouldn't have been given the test case, you might not have figured out how to do it. So yeah, so this is how this question is done, and the implementation is just simple. You just print this value. So moving on to the next question, full path eraser. So in this question, we are given a tree of n vertices rooted at vertex 1. Each vertex has a some value associated with it. And what you can do is, what you have to do, you have to choose a path from starting from the root vertex to some other vertex, or possibly till the root vertex itself. And what you have to do is, so basically you have to remove all those vertices along the path, and whatever disconnected components, whatever forest you obtain, so you have to find the sum of GCDs of each component. So for example, I'll take the example from here. Yeah. Yeah. So suppose we look at this example. Just a minute. Yeah. Suppose we look at this example. And let me just write down the values from the this thing. So it's 3. Let me check this if these are correct. I guess yes. Yeah, these are correct. So yeah. So we are given this values. So basically we have to remove some forest sorry, some path starting from the root node, and our answer will be our answer. So our basically the answer will be the sum of the GCDs of the remaining component. So if I remove this path, my answer will be 3 plus 15 plus 1 plus 5. This will be my answer. Now the question is, how will we go around solving this question? So first thing first, what do we require to solve this question? And basically, okay. So let's start with some observation. So basically, if I okay, so if I want to remove a partial vertex, vertex number 7, I will have to remove its parent. So basically, if you want to remove a vertex, you'll have to remove its parents, all remove its parent also. So okay, so if I want to remove its parent, so is there a way from that I can get the answer after removing node number 7, if I know what is the value of beauty if I remove till node number 5? So if I remove node number 5, my answer is 3 plus 1 plus 1 plus 5, that is 7 plus 3 10. But if I remove node number 7 also along with it, what will be my value? So if I remove node number 7, the value will be, I can write the value as 10, that is the value when 5 was removed, minus the GCD of this subtree, that is 1, and I will add the GCD of its children, that is 5 plus 5. So this will be my answer. Now the question is, how will you how will you do it? So first of all, we'll make a we'll store the GCD of the basically we can at every node we'll store the GCD of the children, GCD of the subtree. So in order to calculate the GCD of subtree, we'll calculate the GCD of subtree, and and after that I will also store the sum of GCDs of the children in that, in another in the node, and basically our answer will be, oh sorry, so at any point if I remove vertex I, the value of beauty if I remove, okay sorry, the value of beauty if I remove vertex I is equal to uh, the value when I remove its parent, just its parent, minus the GCD of that subtree of this vertex, plus the sum of the children. So this will be my answer. Now to look at the implementation, I'll show you my implementation. So so in this DFS, I first calculated the GCD of GCD of every, using DFS. I calculated the GCD of every subtree and stored it in this array GST, and then I ran another DFS to save the sum of the GCD of GCD of the children of a given node. And in this, I basically I basically ran the DP, where basically the DP, so the value of node is equal to value of beauty of node. Beauty after removing a particular node is equal to beauty after removing the parent minus the GC at that point plus the summation of the children. I guess this recurrence is quite simple and understandable by anyone. Now the important thing with this is that I have implemented this question in Python, and Python has the recursion depth. So basically, question has 10 raised 3 into 10 raised to 5 nodes. So if, and also our AI is 10 raised to power 9. So at any point, if I'm given a test case of size which is a path, so my EFS function will keep on going recurring itself, and it will reach a recurrence depth of 3 into 10 raised to power 5 plus log of 10 raised to 9, because I'm also calling GCD function. So I set the recurrence limit to a fairly high level to match with it, and this is the rest of my code, and I passed all the test cases. So yeah, this was this FP question. Now I'm moving on to the last question. It's really a really great question. I wasn't able to solve the question, but I tried out. Like the logic I implemented was absolutely correct. So let's see what this question is. So in this question, we are given an array A and permutation P, and we perform the following operation. So let me just remove this. Yeah. So suppose we are given an array 2, 1, 7, 6, and a permutation 4, 1, 3, 2. So what happens in every operation? So now at position number 1, the permutation points to position number 4. So basically in this operation, 2 will become 2 plus 6, 1 will become 1 plus 2. This 7 points towards itself, so 7 becomes 7 plus 7, and this 6 will become 6 plus 1. Yeah, and in the next operation, basically okay, I don't know where this okay, there's some problem with it. Okay, so 7 will become 7 plus 7, and 6 will become 6 plus 1. I guess there's some problem with the there's some problem with my internet. Okay. Yeah. So okay, sorry for the delay. So suppose I am given in this question we are given an integer n and k, an array of size n, and a permutation of equal size. So suppose this is our n, k, and so what happens in this question? So we are taking any digit. So we are taking the first element of the array. So it points to the position 4. So we'll add the element at position 4 to this. So 2 will become 2 plus 6. Similarly, 1 will become 1 plus 2 because this one points to first location. 7 will be added with 7 itself, and 6 will become 6 plus 2. Sorry, 6 plus 1. Sorry, because 2 is pointing toward this location. And in the next step, what will happen? So this was pointed at this position. So 2 plus 6 plus 6 plus 1. Then 1 plus 2 plus 2 plus 6. 7 plus will remain will even double, and this 6 plus 2 will become will add another. So 6 plus 1 plus 1 plus 2. So this is what you will get. So this is what is happening in the question. Now the thing is, if you naively try to find this, it will take naive algorithm will take. So we need to evaluate 10 to 5 positions with sorry 2 into 10 to 5 positions with 2 into 10 to 5 steps. So this will take a total of uh, this will take 4 into 10 raised to power 10 times, and this algorithm won't work. So we need to do something else. We need to do something smarter for this. So for that, One thing you need to know, and this is very important. I explained this in the previous video as well. Whenever you get a permit, whenever you are given a permutation, the thing is if you run the DFS, there are 90% chance that you will get a cycle. So basically here, this 2 points to this element 4, this points here, this points here, and there is a self cycle here. So basically in the cycle of 2, 6, and 1, only the numbers 2, 6, 1, like after some a large number of k steps, only the elements 2, 1, and 6 will appear in the summation of like a summation of the kth after the kth step in the cycle of 2, 1, 6, and in 7 only 7 will occur. So why do we need, so what if we just separate all these cycles and solve them simultaneously? So let me create another cycle. Suppose I am given an element. So suppose my cycle looks something like this: 2, 1, 7, 6. So basically 2 points to 1, 2 points to 1, 1 points to 7, 7 points to 6, and this guy points to here. Let us assume that this is true for now. So what will happen? So 2 will become 2 plus 1. 1 will become 1 plus 7. 7 will become 7 plus 6. 6 will become 6 plus 2. Now 2 plus 1 will now 2 plus 1 will become 2 plus 1 plus 1 plus 7. 1 plus 7 plus 7 plus 6. 7 plus 6 plus 6 plus 2, and 6 to 2, 1. Now let's go another step beyond, and you will notice one important observation. So 2, 1, 1, 7, 1, 7, 7, 6, 1, 7, 7, 6, 7, 6, 6, 2, 7, 6, 6, 2, 6, 2, 2, 1, and 6, 2, 2, 1, 2, 1, 1, 7. Now if you notice carefully, the 2 comes one time, the 1 comes 3 times, this guy comes 3 times, and this guy comes 1 time. These are nothing but these guys are nothing but the coefficients of a Pascal triangle. Basically these are NCKs. So we can write, so after the kth step we can write the ith element as so if I'm given this cycle, so I can write the kth element as 2 into NC0 plus 1 into NC1 plus 7 into NC2 plus 6 into NC3. Now what happens in the, so if you go one step beyond, there's 6 into NC3. Oh, sorry. My internet is really bad. So 6 into NC3, this is what we will get. Yeah. So this is what we will get. Now, what if we go one step further beyond, we'll get 1, 4, 6. We should get 1, 4, 6, 4, 1. So this 2 will come one time, 7, 6, and another 2 will come like this, like 2 will occur 2 times in that, and basically we'll have to add 1 this over here to find the actual value. Now, okay. So again, back to square one, we had 2176, and after kth step, we will basically need the find the values of NCK to find it. So after like 3 steps, we'll need 2 into NC0, 1 into NC1, 7 into NC2, and 6 into NC3. Now, if you want to find the same thing for 1, if you want to find the same thing for 1, the answer is same, but a cyclic shift of this array. So the answer will be the same, but the cyclic shift of this array, that is, I will have to multiply 2176 with so for finding the value at position of finding the value of what will 2 evolve to after k steps, I will have to find the scalar multiplication of the array. Now for finding the same thing at 1, I will need a cyclic shift. So basically I will need something like this. I'll need the multiplication of this. But if we keep on doing this, we'll basically need n square time to calculate it, because our a chain can be as long, like if I am given like our chain can be as long as the size of n, the 2 into 10 raised to power 5. And if we naively calculate these cycles, it will take 2 into 10 raised to power 5 the whole square time. But we can't do that. I will get a TLE. So even when I came across this problem, I was like stuck. What should I do? Then I realized there is some really great algorithm which is called as fast Fourier transform, or the DFT, discrete Fourier transform. So using that, what we can do is we can calculate every cyclic shift of this these two vectors in n log n time. So how do we do? So basically we take the first vector and take the first vector and we reverse it. So basically 7612 and append as many zeros as of its size. And for the second vector we uh, basically append the second vector to itself. And if we take a polynomial multiplication of this using FFT, so the will result in another sequence of size 2n minus 1, like basically 4n minus 1, and the element of 2n minus 1, 2n minus ith element will be the value of ith cyclic shift if we take the inverse Fourier transform of that. So I mean, so this question is a really important question because it covered a lot of things, like first of all the DFS and DFS and the FFT. Now the thing is, you will implement FFT, but for FFT, like in order to find the FFT, you will need those two arrays, and those two arrays have NCK in it. Now, because you want to find the value of NCK, and you also have to find it modulo some large prime number they have given, whatever, let's call it modulo. We have to find it this way. But we know that A mod B, A plus B mod M is equal to A mod M plus B mod M whole mod M. And this is true for subtraction and multiplication as well. But for division, we cannot write it as A modulo M upon B modulo M. This won't even be an positive integer. So for this, there is something called as inverse modulo. So for B, so if B and M are co-prime, so there will exist a number A into B, like so inverse modulo of B. So such that you in order to calculate the inverse modulo, the thing is you had to find the A raised to power M minus 2 modulo M. So you will get the inverse modulo of this. So basically the property of this inverse modulus A into inverse modulo of B is equal to 1 if is equal to 1 for some for modulo M. So this is the property, and this thing like this B minus like the inverse modulo of A with this inverse modulo of B with respect to the number M is given as A raised to M minus 2 mod M, and this can be proved using a Fermat's-Little theorem. So this can be proved using Fermat's-Little theorem. So basically when you have to calculate NCR, so you will write n factorial upon r factorial n minus r factorial. So basically you can replace 1 upon r factorial by inverse modulo of r factorial, and you can calculate inverse modulo by the method I have mentioned. And now another important thing is So this is how you will make the NCK array. But now another problem is, so if our n is equal to 3 and k is equal to 5, it's like if the size of cycle is 3 and k is equal to 5, so how will our basically, when to find a value at any position, we are multiplying. We have to multiply the cycle array with the NCK array. So basically NC0, NC1, NC2, NC3, no, KC3 basically. But the second array, it depends, like this, the values of the second array depends upon the size of the cycle which we have found. Suppose our k is 5, sorry, k is 4, so our NCK's values will look like this. But if we have cycle of size 3, our this array should look something like something 5, 5, 6. But if it has value 4, it will look something like this, 2, 4, 6, 4. Our NCK array should look like this. But in order to calculate this array, we will need a order of k times, like a time complexity of order of size k, order of k, to find this array. And second thing is, if I am given a size, if I am given n, then so basically the complexity to find out this will be, like you might think, if for n you might have to if you might have to calculate this array n times, so the complexity becomes k times n. But it's not the case. Why? Because if I find a cycle of size 3, and I create this array for it, I can use it for another cycle of size 3. So basically, we'll need to make this array only only those many number of times, as many number of unique cycle as many number of unique cycle lengths are there. So basically, if I have like 1, 2, 3, 4, so let me write a permutation: 1, 4, 2, 3. So here one cycle will be this and another cycle will be this. So I will need I need to make this array only twice. So so the distinct number of this could be, so the distinct number of this will be root n, because uh, if I want to write n as a sum of if I want to write n as a sum of k distinct numbers, so, and I have to maximize k, so you will have to do it via the n into n plus 1 by 2, sorry, some k into k plus 1 by 2 is equal to n. And basically this distinct number of elements will be of so the distinct number of elements will be of the order so the distinct number will be of the order root n. So so basically, so for fast Fourier transform, you will need like something like n log n time, and to make these distinct arrays, you will need k log n times, and for DFS you will need n. So this is the time complexity of the algorithm. Now jumping to the implementation. So I wrote it in Python, and for some reason I couldn't solve this, like couldn't submit the question, get the correct all clear AC on the question. But this was the approach, and this is the approach I thought of, and it is actually the correct approach. I'll have to look into my code, uh, but yeah, like the good thing about this question is it covered a vast majority of topics, and for a long challenge, it was a perfect ending to last question to the long challenge. So yeah, that's it for this. uh yeah, so that's it.